part C.2, formula for die estimation. So in this part, we need to look at some formulas. Our first formula, we want to estimate dies per wafer. Dies per wafer. So we usually use the symbol dPW for this die per wafer. All right, so let's start. First, let's look at a typical situation of a wafer. In a typical wafer, we need to cut as many good dies as possible, right? So that's the goal. All right, so here in this situation, so you can see the wafer, a disk with some diameter, some area, but for a die, from this picture you can see it is a square. But the real die usually is not a square. It is a rectangle. So that difference. So later we need to factor that difference into the estimate. But because usually the dimension difference is not that big, so then people frequently they use the diagonal of square to approximate the diagonal. All right. Let's look at the formula. So with this kind of consideration, so let us look at the formula. Our main formula, dPW equals two terms. The first term, pi r squared, radius, d over 2. Here, the d is the diameter of the wafer. So the radius, pi r squared, pi radius squared. So that's the area of the circle, okay? The disk, wafer, circle, divided by die area. So each die, small die, there is an area. When you do this division, you assume you use all the areas of a wafer to produce dies, right? So when you only look at the first term, when you make the decision, make that division, you use all the area of a wafer to produce all possible dies. That's not accurate, right? Because we know some of the area part cannot be used to produce good dies, right? All these things. We call it edge dies, right? These dies, we call it edge dies. These edge dies should be removed. Okay? Should be removed. So now the second term minus second term, that's the correction term. Because the first term, our estimate, we overestimate comparing with the real number, we do the overestimation. So that's not very accurate. So we want to make correction. We want to subtract another correction term. So this correction term, we will estimate edge dies. So this one, so we need to estimate number of edge dies. Okay, correction term. So how do we how do we estimate that the number of edge dies? Pi times d, diameter. So this is the circumference of the circle, right? The circumference of the circle. The total length of the boundary of the wafer circumference. All right. Then divided by the denominator. This time we use the diagonal of square. Yeah. Here you can see in this formula we assume the die take the square shape. We know that's not accurate, right? Yeah, not very accurate. Here we do approximation because one side then by the Pythagorean theorem, square root of 2. So that square root of 2, then die area, to estimate the real diagonal of a rectangle, that die, okay? That die rectangle estimate. So it's a pretty rough estimate. Yeah. But you can see we try our best, right? We try our best. Yeah, pretty rough. Yeah. All right. So with this kind of understanding, yeah, so I hope you can understand the formula here. Yeah. Understand the dPW formula here. Okay, 2 terms, yeah, the meaning. Yeah. All right, so this is our main formula. So for this video, this is the main formula, dPW formula. After that, we have 2 more formulas, cost formulas. Estimate the total cost, manufacturing cost. Yeah. All right. Here, another, so here there is a tool, online tool that can be used. So people can use this tool to do the estimation. Yeah, so this one is from this website called the Silicon Edge website. So when you go there, so this is the interface of that website. Okay, user's interface. Yeah. So you can set the parameters, default parameters. So this time you can use the rectangle shape die. So width, height, right? So all the parameters you can set. Yeah. So the tool can give you the best possible estimate. Yeah. Yeah. So here I just let you know this tool. Yeah. All right. Next, the formula, cost formulas. Yeah. All right. First, cost of IC, integrated circuit IC formula. Yeah. The ratio of 2 numbers. The numerator contains 3 terms. The first one, cost of die. Each die there is a cost, right? Yeah, first term. Second, cost of testing, initial testing, right? Yeah, remember? So after the wafer, is done, so then some machine need to check each die and mark. If there is a defective one, put a mark on it, right? Yeah, that step, there is a cost. Cost of testing. Yeah. Then the third term, cost of packaging plus final test. Yeah. Think about that step, the last step. Yeah. So after all the good dies pass the initial testing, all right, so then do packaging, right? Packaging, there is a cost. Delivery, deliver to the customers, right? Shipping, delivery to the customers. Then after the customers, so they receive, because they will put in the product, okay? Before they put there, they need a final test. So they need a special device to quickly do final test. Because during the shipping, transportation, that long period, some of the dies could be defective due to some reason. Temperature, shaking, all different factors considered. So there is a final round testing before each chip is placed inside a computer. You don't want to put a, malfunctioning chip in a computer. You don't want. So before you put there is a final test. There is a cost. Okay? So you put all those costs together, then you spread that number. So you spread that number. So here, not spread the number. So here, because the final test, there is a yield, right? The final test, there is a yield percentage. So then because you throw away the bad one, you only consider the good dies past the final testing, right? So that yield. So then you need to scale your cost after this division on final test yield. Hopefully that percentage is pretty high. Otherwise, your cost will be much bigger. If that yield is pretty high, so then your total cost is okay. All right. Then cost of die is given in this formula. Cost per wafer. Each wafer there is a cost, right? Then the wafer cost will be spread on all the good dies. So bad dies cannot carry any cost. Bad dies cannot carry any cost. Throw away. Okay? So then the cost must be spread over all the good dies. So that's the reason we have this formula. Cost of wafer over number of good dies. How to calculate number of good dies? dPW times die yield. Right? So that's this formula. All right. So we get these formulas. Later, we will use these formulas to do a lot of calculations. All right, so next, another formula. So this time, we use another empirical formula to estimate die yield. All right, so the formula name is called Bose-Einstein formula for die yield. The reason we call this name Bose-Einstein formula because they use the Bose-Einstein statistics model. So this Einstein is that famous Albert Einstein. So they developed a very special statistics model. So it's called a Bose-Einstein statistics model. And this formula is based on that model. You need to do some assumption. The assumption based on that model. All right. Assumption here. Defects, assumption. Okay. Defects are randomly distributed over the wafer. That's pretty reasonable. Defects distributed randomly. And the yield is inversely proportional to the complexity of the fabrication process. Inversely proportional. Okay? If the complexity is, very complicated, the yield will be, right? Yield will be smaller. Too complicated, complex, there is a coefficient, there is a number. If that number is big, then you need to get smaller yield. That's pretty reasonable, right? Yeah. Too complicated, so then yield will be low. Yeah. All right. So based on that model, the formula is like this: die yield equals wafer yield times 1 over inverse proportional, right? 1 over then this formula. Yeah. Parenthesis 1 plus defects per unit area times die area. This number, you calculate the number of defects on one die, right? A number of defects on a die. So 1 plus that number. Then calculate that number to the n power, nth power. That n not necessarily integer. Usually it's not an integer, okay? Because it's the process complexity factor. So it should not be an integer. So usually it's a non-integer number. Yeah. Actually, in our textbook, it uses 13.3, just like that, because it's an empirical formula. So it is not a formula derived by some math calculation. It's not that, based on model assumption, doing experiments to check if the formula is close or not. Empirical formula. Very hard to do some very rigorous calculation to get it. Alternative version. Using the same model, but so if you make some slightly different adjustment, you get a different version. All right. So this version, then we will change. We use another parameter, alpha, this time alpha, raised to negative exponent alpha, but there is a denominator, defects per unit area times die area divided by this alpha. So you can see these two formulas quite different, but they approximate die yield in different ways. Because empirical formulas, so it may not be very precise. Okay, at some extent close to the real numbers, because you use it to estimate die yield number. All right. So alpha, a measure of manufacturing complexity. Also manufacturing complexity and process complexity factor. See, just some special parameter connect to the process complexity, right? So it's very hard to define those numbers, parameters, the meaning of parameters, because it's based on experiments. Okay, all right. And a good estimate, alpha equals 4.0. 4.0, okay, you put 4 there, so you get a pretty good estimate. All right, because many times, many formulas, it is very hard to derive them rigorously using the rigorous math. We can only do experiments, try to get a close estimate for those formulas. So here we have the case. That's the case of that. All right. So we finish part C.2. After this one, then we need to do some computation examples. So I want to use several examples to show you how to use these formulas to solve some related questions. Yeah. All right, so let me stop here. Yeah.